Hello, today we will look at the heap data structure. Heap data structure is a complete binary tree. A complete binary tree is a tree where all levels are filled except possibly the last one. The leaf nodes are filled from left. Every node in a heap must satisfy the heap property. This is an example of a complete binary tree. There are two types of heaps possible. One is max heap, which is explained here, and the other one is min heap, which is quite similar. So for every node in the heap, the child must have values less than the node. And here's an example. Here the children are 23 and 12, and they both have values less than their parent, which is 34. Before we move on, we need to know an operation called heapify. It is an operation to modify the tree to satisfy the heap property. Let's define a function heapify which takes parent as an argument. We will check the values of the parent and its children, and we will replace the parent with the maximum value node among these three nodes. Let's see an example. Here we have three nodes. We will check for the max value. The max value is 12. It will be updated to 34, and it will remain 34. So the maximum value node is 34, and we will swap parent and this node. So 12 and 34 will be swapped. Now the heap property is satisfied. Heapify is used to convert a complete binary tree into a heap. Since it's a complete binary tree, it is optimal to represent the heap as an array. The array here represents the complete binary tree, which is shown below. Let's see how we can convert a complete binary tree into a heap. We will start with the first non-leaf node from the end, and we are talking about the array here. So the first non-leaf node will be 2. We will apply heapify operation on it. The max value is 5, so we need to swap. We'll move to the next. Compare the three values. The maximum value is 9, so we will not swap because 9 is the parent itself. Move to the next. Compare the values. The maximum value is 9, so we will swap here 3 and 9, and the swap is done. Now we have traversed all the non-leaf nodes, but there is a problem here, and you can see this node does not satisfy the heap property. The reason is, after swapping we are ignoring the resulting subtree. To solve this, every time a swap occurs, we need to apply the heapify operation on that child too. So let's go back, compare the values. Maximum value is 9, so we will swap them. After swapping, we will apply the heapify on the child node too. We will compare the values. The maximum value is 4, so we need to swap the values, and we need to apply the heapify operation on 3 as well, but since it's a leaf node, nothing will happen. Now we can say the tree is a max heap. Let's look at the heapify code. In this function, we have the index of the current node, our array, and the total number of nodes. We will first find the left index of the left child and the right child, and we will assume the largest value node is the parent itself or the current node, and we have two if statements to update the largest value index. If the largest value node is not the current one, then we need to swap these nodes and apply the heapify operation on that child node, and this will happen recursively. Converting an array into a heap takes big O of n. It looks like it should be big O of n log n time, but it can be proved it's big O of n. Let's see how insertion works. Suppose we want to insert 10. We will add it to the end, and then we will keep swapping with the parent until its value is larger than the parent. So we will compare 5 and 10 and swap the values. Then we will compare 9 and 10 and swap them, and no more swaps are possible. So the time complexity here is big O of log n because we are traversing only the height of the tree. Here is the code for insertion. We will insert our value to the back of the array. Then we will find the index of the current node and its parent. And we will keep running this loop until our current node is not the root and the value of the current node is greater than its parent. And we will keep swapping it. Let's look at deletion. Usually heap only gives us access to the root node, but the same logic can be applied to any node. And we will swap the root with the last node. We will delete the last node and apply the heapify operation on the root. So compare the values, the maximum value is 9, so we need to swap. These values will be swapped. And we will apply heapify on the child. Compare the values, the maximum value is 5 here, so no swap required. And we will stop. Time complexity is again big O of log n because we are traversing the height of the tree. And this is the code for the deletion. We are taking the last leaf node's value and putting it in the root node and then deleting that last node and applying the heapify operation on the root. And that's all about the basics of the heap data structure. And here are the few uses of the data structure. First one is heap sort, and the other one is priority queue, and there are more use cases. I hope you liked the video. Thank you for watching.